We are recording.
Okay, so thank you very much. Thank you everybody for staying here again after 8 hours of lectures. So before starting the topic of today, I thought I will give you a quick, let's say quick sum up of what we have done, let's say in my first lecture, because I feel it was too rushed, and I mean repeating is never a bad idea. So I want to inaugurare. I want to start a new format. As you can see, there are questions covered by black, and I invite you to answer these questions. So the first question is this one. What is the aim of this course? It's very important in motivating you in listening and trying to understand the way you should try to understand. And I'm waiting for an answer. And we have 4 hours left. I don't want to spend all 4 hours in waiting. So what do you think, what do you expect from this course? What do you think it is for me, the aim of this course?
Don't be shy.
Making you in 20 hours the best expert in the world in differential geometry. Is this the aim?
We hope. That's our hope.
So Roberto, do you remember what is the aim of the course?
Maybe just to get a flower of this topic and to get interested in, excited in studying.
Get the flower, interested and excited. Let me check the correct answer.
No.
Well, more or less, yes. The aim of this course is letting you become excited. Yes, that works. In particular, I want you to become confident that you can learn it. Okay, so you can think of this as a second level aim. You don't have in these lectures really to learn the topic. You have to learn the fact to become confident in the fact that these kind of things are not so ugly, are not so difficult, are not so ununderstandable, okay? So, in order to do this, let's say from the beginning what we are talking about. We started saying something very, very strange. Tangent vectors on Rn are not vectors as you are used to think about, but they are just derivations. I mean, not just, they can be seen in a different way. That sounds kind of more complicated, but it will be, trust me, very useful in the future. So from now on, for us, on the first lecture actually, when I say tangent vector, I invite you to think about the derivation, the derivative, directional derivative on functions. Okay, so if I'm here in this point P, I have this direction. I take a function R square, and I take the derivative in that direction of the function. Okay, and so I have a map from functions to R, because I'm evaluating the derivative in a point. Or if I'm not evaluating the derivative in a point, I have a map from functions to functions. Okay, by the way, a tangent vector is a derivation. Just memorize this, okay? You have a direction and you take the derivative. Okay, now, Tensor. This is a word very used in any topic. Tensor, nothing to be scared about. It's just a new name, a fancy name for a multilinear map on the tangent space. Now, I know that this seems, why should I be interested in multilinear maps? Well, for several reasons. I mean, if you have a vector space V, a metric, for instance, is a map from this Cartesian product to R. I mean, a metric is a way of taking two vectors and telling how much they are with respect to the other. It's a way to tell the projection on one on the direction given from the other, right? It's a very important notion. Well, this is a multilinear map. Actually, you could probably bilinear map on the vector space V. So multilinear maps in general are very important. And for this reason, we have a special name for that. Okay, tensor. Now, between multilinear maps, I mean, they are all equal, but there are some of them that are more equal. That is the one that are alternating. For the topic of today, this is actually what we are going to study today. Multilinear maps which are alternating. Alternating means that if you swap the argument and you take, for instance, this quantity, then you obtain the same quantity but with the sign reversed. Okay, this means alternating. Of course, if the map is defined on the V times V times V, then alternating means that whatever swap of arguments you take, you change the sign. Okay, so these alternating maps are called forms. Okay, so a form on a vector space will become a differential form next. A form on a vector space is just a multilinear map which is alternating. Okay, so you see, I'm just giving you some terminology. Okay, now assume you have two maps. What is the easiest multilinear map on a vector space? It's just a one linear map. Okay, so we are interested in particular, of course, on linear maps on the tangent space. So let's take two linear maps on the tangent space, which is a vector space, okay? Just take two linear maps on one vector space. This vector space is the tangent space, but what I'm saying holds for every vector space, of course. I'm telling you that there is a very natural way to multiply them. Something which is called tensor product, another fancy word to say something very simple. The tensor product between two linear maps is a bilinear map, defined how? And this is the next question. So I'm asking you, if I have one linear map, another linear map, there is a very natural way to build a multilinear map on the product of the domains of these two linear maps. That is a bilinear map, which is this way. It's very natural, I mean. And I'm still waiting for the answer. Come on, guys, don't be shy.
Omega of V dot tau of W.
Dot, what do you mean by dot? Omega of V is just a number.
Okay.
So, what do you mean by dot? simple product, which is the scalar product. Of course, it is a scalar product, but don't think more difficult than it is. Okay, guys, this is just a number. This is another number. You want to define the multiplication between two maps. This is the same product you have for functions, actually. Okay, you call in a fancy way for linear maps, you call it tensor product. Okay. Now, I'm asking you, do you think that this map you obtained is alternating? It isn't, because if you swap the argument, then they completely change, right? Well, sometimes you want a product making an alternating multilinear map, because remember, we are interested in the more equal multilinear maps with respect to the others that are the alternating ones. Okay, so next question is, can you guess a way as natural as this one to obtain an alternating map from two linear maps? So I have one form, another form. I want to obtain a two form that is a bilinear map, but additionally, I want this bilinear map to be alternating. What do you do? There is a barrier.
Yeah, difference.
Take the difference, exactly. Just like above, but just take the difference. You see, this one is not alternating because if you swap the terms, you obtain another piece. You want to remove that piece, and so you subtract it. By the way, this is a canonical way to obtain from a general multilinear map a symmetric part, just take the sum, and the alternating part, just take the difference. Moreover, if this map is multilinear not with two arguments, but with three arguments, you have to take these differences between every pair in the possible three arguments. And this makes a ugly notation. You have to act by permutations on the rank of the tensor, okay? But this is a very, very easy. I mean, the rest is just notation and for technicalities. I mean, this is the important part. Okay, next. Now, since we are interested in linear maps, I'm now telling you that there is still a very canonical, so canonical that it's called a tautological construction of obtaining from a function, if you have a function on an open set of Rn, let's say, then you can build a tautological linear map on the tangent space in a point to this space. So what is this map? First, notice that in order to give me a map on the tangent space, you have to tell me, given a tangent vector, this one is a tangent vector, where is this tangent vector going? Okay, so you just have to cook the ingredients you have. The ingredients are just one function and one tangent vector. And I want you to give me a real number. You have a tangent vector and a function. What are tangent vectors again? Directional derivatives in the point. So you have a tangent vector, you have a function. What do? You take the derivative and you compute in that point. Let me check. Here we are. Yes, very good. You see, I mean, do you agree that this is very easy? I mean, we are just cooking up new terminology. There is no new math here. This is just a way of setting up notation terminology, but this point of view is the point of view that make all differential geometry explode and start. Okay, this linear map is a map that you already knows very well. You use it always. It is called the differential of the function. It's the famous, or maybe infamous, differential df. The total derivative, the total differential, and several names. And you know what? Now something very important in your lives is going to happen. You are going to understand, to give a meaning to something that up to now was just a symbol. And this is the fact. On Rn, there are special functions. Which one? From Rn on R, I have said if you have a function, you can have the differential of this function, right? Now I'm asking you, can you tell me a very special function on from Rn to R? Actually, n special functions.
Coordinates functions.
Very, very special and very, very easy.
Coordinates.
I'm asking you one function. If you have to think about one function, what were you saying, Roberto?
Norm.
The norm, too complicated, much simpler.
Coordinate.
This is the element. The sum, too complicated. Think easier. The first, the projection in a more technical terms. Do you agree that this is a function? Okay. And if you have a function, what can you build? The differential of the function, right? Which is a linear map from the tangent space to R, right? So take this function and build the differential, and you have the famous dx, the infinitesimal increment of the independent variable in one direction. Yes, this is the differential in one direction, and of course you have the differential of the other projection and so on. So you have this set. What is this set? Because I mean, it is a set contained in the set of, well, not all differential, all linear maps from the tangent space to R. Okay, so you understand this space is very important. The space of all linear maps from, let's give it a name and a symbol. Okay, the symbol we use is the dual space. We take an asterisk or sometimes a V this way, but I prefer the asterisk. Okay, and this means the linear maps. So now you have a meaning for the part that you put into integrals. And there is a reason for this, of course. Very good. So let me check. So we have this part. These differentials are a set in the cotangent space. Well, when you have a vector space and it's dual, there is a notion of the dual basis. If you do some linear algebra, it means simply that when you evaluate this on the element of the basis of the vector space, you obtain 1, 0, 0, 0, and so on. In formulas, you obtain the Kronecker delta. delta I, J. Again, a complicated notation to express something very simple, okay? So, by definition, yes. Let's try to check this, just to understand how it works. I'm just telling you that the x1, which is a linear map on tangent vectors, so evaluated on the tangent vector d in the x1, I'm telling you that this is 1, and on the other is 0, okay? By definition, yes, but try evaluating this. First, this is a tangent vector, okay? You see, I'm writing an operator on function. Yes, tangent vectors are derivations. This is the tangent vector given by the derivation in the x direction. Okay, so it corresponds to the vector 1, 0, 0, 0, and so on. Okay, but I prefer this way, because in this way, by definition of differential, this is just the directional derivative in this directional, that is this derivative of the function, and the function is x1. Oh my God, it works. Okay, and of course, if you have x2 here, you have 0. You see, I mean, nothing really difficult, just by definition. But if you think about it, in 10 minutes, I have given to you 10 new definitions. So it is understandable if you feel overwhelmed and you feel, no, I need time to get everything. Yes, aim of this course is to get you confident that you can learn all of this, okay? If now you are not memorizing everything, it's not a problem. But anyway, this is just the very, very beginning. So stay tuned, brace the belt, and let's go on. Now, we have functions, and on functions, we can take the differential of functions, obtaining a form, okay, a linear map. What if I tell you that we can go on taking differentials, and from one form obtaining 2 forms, and then obtaining 3 forms, and so on, in a very, very natural way? Let's say I have one form, one linear form, okay? One linear map on the tangent space. Since this is a linear map on the tangent space, this will be, for instance, this is just an example, some function calculated in the point P times one vector of the basis of your vector space. We just say that linear functions have as a basis this, okay? This is a basis for linear functions. So for instance, if I take some function evaluated in a point P, so this means a number, but a number coming from a local function, times the differential of, let's say, x3, for instance, evaluated in P, this is a one form, okay? And if you want to define the differential of this one form, how can you do this? Well, just define the coefficient that you know how to do. The differential of this function, it's a one form, and here you have another one form, and you know that you can do the wedge product. You see, we are putting together all the definition from previous slides. This is a 2 form. That is, I recall the definition, it is a bilinear map on the tangent space in P, which is also alternating. It is alternating because of the wedge product. The wedge product is just giving alternation, okay? And in this way, we have a map. The differential instantly becomes several maps, actually. To be more formal, I should write dk. Okay, the differential on 0 forms, the differential on 1 forms, the differential on 2 forms, and so on. Mapping K forms into K+1 forms. And in this line, I'm giving you another definition implicitly. This is the notation we use for alternating multilinear K form. Alternating multilinear maps. When I say form, I mean alternating. Okay?
So it's a map of maps.
Yes, in some sense. But just think, this is just a vector space. I mean, the fact that the maps on a vector space are a vector space should ease you out to think about it. Of course, if you think this is a map between a space of maps, and what maps? These are multilinear alternating maps. Come on. And I'm sending them over them. It's ugly, okay? But if you think this is just a vector space, so this is a map from one vector space to the other vector space. And you can guess this map is linear, as it's a map from vector spaces and so on. Okay. So, how many questions? Now, the big one, this is not a question, okay? There are no question marks, just the final surprise. Now, the question is the following. Let's sum up all we are saying. So let's fix a point, and let's check if you have memorized some of the several vector space we have in this point. So I want you to name some vector space in the point P. The first one, well, of course, the first one will be the tangent space. Oh, and also the second one is the cotangent space that are linear maps. Then, can you... Say again?
Differential form.
Oh, so you would take the differential and you would take the image of the differential of the space. That's a very good point. It's not included, but we have dots. Okay, so you are saying, I can write your suggestion, you are saying the image of dk in the language of before, that is a subspace of lambda k plus 1 of t p star. Correct, but this means that, for instance, this is also another vector space. Okay. So this is a very important space. If you think about it, you know the name for these objects. These are the objects which are the differential of something. You probably call them exact forms, or not. I don't know if you. I mean, you needed to integrate them. Okay. And but by the way, we are not touching this part because this is the RAM cohomology. It's the part we are skipping. It's the last chapters of the book. Very important. But let me uncover this answer. Okay, so we have this one. This is what we were talking about. That is, this lambda k can be taught as the lambda product of the single cotangent spaces. Okay, but you can have also, why limiting to alternating maps? You can just take multilinear maps. Okay, so this is another vector space in P. Okay, it's a space of maps on the tangent vector, but it is a vector space. So from one vector space or two vector spaces, we can build several other vector spaces, right? Well, this one, I don't ask you to guess it, but just to show you that we can do something more complicated. If this is working, please, yes. I could take the endomorphism from the tangent space to the tangent space. I mean, for the moment, these are maps from the tangent space to R. But I could take maps from the tangent space to the tangent space itself. I mean, between two different or equal vector space, I can have linear maps. When I say maps, I mean linear maps.
The maps are the vector spaces.
In this case, the new vector space is the one given by the maps. You can ask, who cares about this? Well, for instance, think to there is a very important object in differential geometry arising from this notion. Think about when you have the complex numbers. You can multiply by I, the complex unit, and this is just the rotation on 90 degrees. Well, this rotation, now you know that R squared, complex numbers, is a manifold, and when you take a vector in a point and rotate it on 90 degrees, you are making something on the tangent space. What is this rotation? Is a map from the tangent space to itself, non-trivial map, I mean, with a very deep geometric meaning, that is the complex multiplication. All the theory of holomorphic functions, that is functions admitting a complex notion of derivative, arise from here. And this is the very famous complex geometry, complex differential geometry. It's a geometry where we are concerned with differential manifolds equipped with such a structure, an element of this space, for every point P. Okay? And now, the big step in the notation and terminology. I ask you to tell me if you agree on this. What is this? Yes, should be a vector space, but what is the first? Okay, so apparently these are tangent vectors. And what is this symbol again? What is this symbol denoting, doing?
Tensor product.
Is the product between? But I mean, you have a definition for this. The definition was given in a certain environment, which apparently here is not so.
Where involve the functions going to R.
Exactly. Here and here, you need multilinear functions. Okay? Here you have multilinear function. One linear function, actually. But here, no. So what does this mean? So my question is, can you guess so I'm saying that the tangent space, these tangent vectors, in some sense are just like this is contained in maps of a certain type, okay? This is also contained in maps. I mean maps on, okay, maps, nothing else. I'm telling you this. Have you ever heard the fact that a vector space and its dual, that is, maps on the vector space, are isomorphic? Okay. The reason for them being isomorphic is very trivial. They have the same dimension. Every space of a fixed dimension, vector space, I mean, is isomorphic to Rn. Okay. Have you ever heard the sentence, but this isomorphism is not canonical? Means that in order to have this isomorphism, you have to choose a basis. Once you have a basis, then you have the isomorphism. Otherwise, and if you change the basis, the isomorphisms are different. Okay, the maps are different. Well, but we can do the same. We can say that this is isomorphic to, it's dual. Oh my God. We are really exaggerating now. So these are linear maps on linear maps. You feel entangled, right? You can't imagine it. Okay, don't imagine it. It's just a vector space. Okay, just a construction. And you know what? If you compose these two maps, this map that you obtain is canonical. Doesn't depend anymore from the choice of the basis you have used here. So this means in mathematical language that a space and its double dual are completely the same. You can talk about one or the other. Okay?
Can you say again? Always or in which?
Only in finite dimension. Okay. Always it's contained.
In a finite dimension?
Yes. In differential geometry, I mean, linear algebra is also a finite dimension. There is infinite dimensional differential geometry, which has, as you can imagine, several other problems, and you need several different notions from functional analysis and something like this. Okay, so for us, these are equal. And then these are maps on forms. Okay, so this means since this is something star, these are maps on something, we can take the tensor product. Don't think how to express it. If you have an exercise, then you try to apply the definition. But for the moment, just understand, trust that everything makes sense. And it's not difficult. It's just a mess when you are trying to write explicitly things. But depending on the point of view, can be also very, very easy, very tautological. Everything is tautological, actually. Now, this means that we can take the product, the tensor product, between several tangent space and several cotangent space. What does this mean? What is, for instance, phi element of tangent space, tensor tangent space, tensor product, cotangent space? What is this? First, it's a multilinear map. So, how many arguments? 3. So it means that here I can take one argument, one argument, another argument, and omega 2, omega 1, and another argument. These 3 arguments, where they belong to, where they live. What is this? What is a tangent vector as a map? A map from form to R. So what is this? It's a one form. And the same omega 2. And what is this? These are maps from the tangent space. So this is in the tangent space. And this is why I denoted them by omega 1, omega 2, and x1. Okay? And if you express them in coordinates, if you want to find, for instance, this phi computed in dx3, which is an element of a basis for TP star, and dx2, which is an element of the basis for TP star, on dx1. What is this? And sorry, let me call, instead of phi, this, let me call T, capital T. Well, these are the components of this vector, because you know what? This is a vector space of multilinear maps, of course, but this is a vector space, so vectors have coordinates, and this is the coordinate corresponding to 3, 2, 1, where 3 and 2 denote the part given by tangent vectors. For reason that we could investigate what we aren't, this part is called the contravariant part. This is related to the functorial language, contravariant part. And this part is the covariant part. And this means that 3 and 2 are the contravariant indexes. I'm not sure, but I think they are put here. And the other is above, the covariant index. So you already know everything about this. You already use it. Just you look at everything in local coordinates. Because you work on Rn, and so you have canonical basis. You always use this. But you know what? On manifold, you don't have canonical coordinates. It depends on the point you are. It depends on the local chart around the point that you are looking at. Okay. So this is the tensor. These are tensor with key contravariant and L covariant indexes, transforming with a certain rules. This is about manifold later. And you know, you can say also, I can take a tensor where the covariant part is actually alternating, fully alternating in all the L components. This means that the covariant part is an L form. And you would say, okay, my tensor has L covariant fully alternating indexes or something like this. Okay, so you see, you already use this kind of notation and language just in coordinates. Okay, now, up to now we were talking, but let me check if, I mean, are you there, everybody? Can you confirm me that my voice is arriving to you, because nobody's speaking?
Yes.
It's okay and clear.
Yes.
Oh, yeah. Okay, can you tell again? My audio is...
Yes, I can hear you very well.
Okay. So, but Roberto, you had the audio turned on? Oh, mine was turned off. Okay, so sorry guys, if somebody tried to answer, my audio was off. So.
And Marino gave an answer on the chat.
Oh, okay.
It was at 2:50.
Okay, so I really apologize, guys. If you think I was ignoring you, was not the case. I was just with the audio switch off.
No problem at all.
Okay, so please, if you have questions about everything up to now, is everything clear, more or less? Okay, so please interrupt me if you have any doubt. Now, still a small leap in the space, literally in the space now, because up to now we were talking about the tangent space in a fixed point P. But I mean, I can also take if I have, for instance, a vector, a tangent vector in this space, I can take for every point P, I can take this tangent vector. This means taking a tangent vector in several different points, right? And you know this is an object very important, very interesting. This is called the vector field. Okay, so a vector field is just a choice of tangent vectors, but with the point moving. And of course, I ask this point move in a smooth way, okay, in some sense that should be specified. And we are going to specify it right now. We did actually in the first lecture. To put it in a more important language, I can take the union of all the tangent spaces. Think about it. Take the union of all the tangent space. You are just taking these lines. These lines are vector spaces. The fact that that vector space is represented by the fact that they are lines, so straight lines, okay? So they are linear. And I have not enough room on the screen to put here a plane or an n-dimensional vector space, okay? So I just put a one-dimensional vector space and I tell you this is Rn, okay? This is an n-dimensional vector space. And there is one of them over each point of U. This is U, okay? This part, the base. And so you see a point here is just the choice of a point in U and the vector in the tangent space in that point. This is important. It's not just a tangent vector. It's a tangent vector on this point, on the first coordinate. Okay? Well, if you do this set, it's clearly a product. Okay, this is just the product of U times Rn, so nothing new. U is an open set of Rn, so this is just something living in the R2n. In a sense, the dimension, the original dimension of the space you are looking at now is doubled because you are adding for each point other n dimensions. Okay, in a just qualitative way. Well, we say that this set with this topology, I mean, with this this notion of neighborhoods of points and so on, we call it the tangent space. Okay, so no more, the tangent bundle over U. Bundle means just like a bundle, a gomitolo in Italiano, means that on every point there are these fibers, okay, and they are all together, they are close with each other, and so on. With this new object, with this point of view, a tangent vector, when considered for every point P, becomes just a map this way. But be careful, a special map. A map that when I take a point P, its image cannot be a tangent vector in a point Q. Must be a tangent vector in the same point P. Okay? And this is what is called the vector field. And in general, when I take this condition, a map that is in some sense reversing the projection, because the projection in the other direction is sending P V into P. Okay, a tangent vector in P is tangent to the point P. And so a vector field is just reversing this map. I'm talking about this map more in general. Reversing in which sense? And this is the next question. And by the way, the terminology for a map from U to the tangent bundle to U such that over a point P there is an element of the corresponding tangent space in P, these kind of maps are called sections. Okay, new terminology, something more to put in all the big pen full of new notions. But oh yes, the question here is about terminology. If you remember these elements, that is sections of this projection, they are called the differential K form, and as you can guess, these are the topic of this lecture. They are the very important. I mean, I don't want to be forced to use such a long sentence to describe them. Take a differential K form that is a section of the alternating K powers of the tangent bundle to U. I mean, there is a symbol that we use, which is this denoted. It's not a definition, just the symbol we use to denote differential K form that we will use very often. Of course, will be a symbol with a K, and they are differential K form on U. Yes, please. It's a Greek letter. I guess the last one, capital.
It's lambda kappa to omega.
Omega,
Okay.
yes.
I would have said lambda kappa to star.
So you would say lambda kappa T star U.
Yeah.
Sorry, kappa, not star. Lambda kappa T star. Actually, it's not lambda kappa T star. Are maps from U to lambda kappa T star U. So you see that notation is more complicated, and not only these are not only maps but sections of this. So the notation actually is, if you want to denote them by section, you should write section of over U of lambda kappa T star U. This is the notation. This is the symbol we use for sections. Okay, and all of this, the shortcut is omega KU. Notice that there is no more mention to the cotangent space. It's implicit in the word omega. Omega are differential forms. Differential forms means forms. Forms means sections of this. Differential means that as a map, as a section is C infinity. It is smooth. Okay. Okay. Now, what we are using all these things for? This is the summary for manifolds. Up to now, we were just talking about tangent vectors, forms, multilinear maps, tensors in general, but everything was on a subset U in Rn. Now we put all pieces together. We take a certain family of spaces, of sets, very particular, sets that around every point can be described by an open set U, which is homeomorphic, means that is equivalent with respect to continuous maps. There is a continuous map from here to Rn, which is invertible. So from the topological point of view, U is Rn. Okay? And we ask that, of course, this is a certain map. Okay? This is called a chart around the point P. Now, imagine that we have another chart around the point P. We ask that whenever we have two such maps, phi and psi, going to Rn, they are invertible, okay? So I can use them in both directions. When I go from here to here, or vice versa, I'm requiring that this is a smooth map. This is a requirement I'm doing on these maps. Okay, so my set is covered by patches that are indistinguishable from Rn. Okay, they are homeomorphic, so they are just Rn. And whenever I have some non-empty intersections of these two sets, I have a map from one Rn to the other Rn. Okay, I require this map, which is of course an homeomorphism, okay, because it's a composition of continuous and with continuous inverse maps. I require this map to be smooth, that is to have derivatives as many as we like. Okay, well, this is what is called a differentiable manifold. This object is called differentiable manifold. And what is it used for? Well, it is something that locally is exactly like Rn. So you know what? Whatever construction we have done before on Rn now can be made on a manifold. Just take a point P. Take this point P. Let me do this. So this is the manifold, okay? And we want to define tangent vectors on this manifold, right? We start from a point P, and we want to define tangent vectors on the point P, okay? We have no idea on how to define tangent vectors on this set. This is an abstract set, but we know its property is that there is a certain U here, which is Rn. Okay? And so I know that in Rn, I can take tangent vectors. So I can say a tangent vector here is a derivation seen in Rn. Okay, there are technical details, of course, but the most important one is the following. To tell that these are derivation on Rn, I actually have, this is U, right? So I have to take a function from U to R. And what should I do with this function? This function is going through my chart, which is phi, let's say phi U, okay, to Rn. If you take the inverse, okay, it doesn't matter because they are homeomorphisms, then you can compose with R, and then this F gives you another F, which is actually F after phi U. Okay, but in differential geometry, after a certain time, you just ignore this. You say, this is F, we are looking at F just locally, just in the chart, okay? But for the moment, let's use the whole thing. And this is the map that I'm taking the derivative of. So I'm taking the derivative in the, let's say, direction x1 where x1 is here, not here. But of course, through phi, it is also there. I take this derivative and I compute it in P, not really in P, in phi of P. You see, it seems very complicated, but geometrically, I'm just looking at everything through this phi. Phi is my dictionary to look things in Rn. But now there is a potential problem, because, I mean, in this point P is in U, but maybe there is another set B, which is containing P also. Now, I have made the derivative this way, okay? Now Roberto arrives and he does the same computation, but unfortunately the first open set he was choosing was V. So he's doing the derivative of F after WV in the, not X1, in the X tilde one, because these are coordinates on the other space computed in phi V of P. If these two numbers are different, then this definition doesn't make sense, because it depends, we would say, this definition is depending on the choice of the chart, and so it's not working on manifold, it works only on Rn. Well, you know what? This condition, exactly this condition, that the transitions between charts are C infinity, means exactly that if you do your duty, your computation, the two numbers are the same. So we have an intrinsic notion of derivatives. And the same works for differential forms. Okay, you take the differential forms in that point and you can glue them all together thanks to this notion of transitions to be smooth. Okay, guys, it's really very, very plain. I don't want to say easy. I mean, this is a lot of things, but the idea, the principle is really easy to understand. Of course, if you want to check everything, there are millions of details I haven't told you. Okay, that you should double check to be sure that everything works. But yes, everything works. Okay, and so finally, what do we have? We have the tangent bundle, denoted by Tn. Please notice that now N is no more a small set, a U, an open set. N is the whole manifold, it's global. Okay, and what is this? This is the union of all the tangent spaces. What are these tangent spaces? We just define them. And what is this union? Well, this union can be seen locally, and so I can say that this union locally is just U times Rn. So points of this tangent space, when looked at through the magnifying glass of charts, locally they are just this. So a tangent vector is just the choice of a point and a vector on that point. Okay? And if I take another glass, that is another chart, and I look through another open set, I obtain the same point. The same object as tangent vector. What does it mean, the same object? That as a derivation of functions, it works in the same way. Okay? Well, final question. What is the dimension of this tangent bundle? Assuming that locally this is just U times Rn. What is the dimension of U? U was an open set.
Yes, an open set.
And so its dimension is n, and so the dimension of everything here is 2n. So we are just saying that the tangent bundle is by itself a differentiable manifold of dimension 2n. And you know what? You can do also the cotangent bundle. And you know what? You can do also, for instance, the bundle of K form, not U, but N. Okay? This is the bundle of differential K forms, and so on. So here you have a map over N, and if you take sections of this, you obtain K forms, which are denoted by omega K N, just as before. We are gluing everything together. Okay, this was the warm-up on the previous page. And I guess, what's the time? 22:04. Okay. Well, I think it's worth the time. Okay. Can you warn me at 4:30 so we can have a break? Okay. Okay. Skip all this part. This is okay. This is the introduction. Are there questions up to now? Okay, so, well, actually, this first part is more or less, we already said everything. Let's go through this, okay? But you will see that everything is already said. So, first of all, in this section, we are describing differential one forms. We already know what they are. Okay, differential one forms. One means that they are in the cotangent space. So if M is the manifold, we have the cotangent space M. And differential means that I'm looking at them not just in a single point P. I'm just looking at them over every point of the manifold. And so over every point of the manifold, I have one cotangent vector. Well, a cotangent vector is also called a covector. So, terminology. A covector at P is just a linear map on tangent vectors, what we have called the one form. Notice that form means an alternating multilinear map. In the trivial case of one linear map, that are linear maps, every map is both symmetric and alternating. So this is why I'm calling linear maps as form. They are just maps, yes, you're right, but they are considered one form. And more, functions are considered to be zero forms. Okay, if you do this, start thinking about this, it works and everything is easier. Anyway, you see here, I wrote that covector P is a linear map on tangent vectors, okay? And then a covector field called also a differential one form, or called also a one form on M. You see that everything we already said in the introduction is a function assigning to each point a covector at that point. I think you are now completely able to understand this sentence. Okay. Now there is a new notation. I don't remember if I used this on the first lecture. When you see check, is an invitation for you when you are studying through this material to ask yourself, what is this symbol? Gamma of Tm. What is Tm? The tangent. What was the word? Bundle. What is a bundle? Let me go through the book and let me check. Okay. So check means stop and ask yourself if you understand the notation and the meaning. What is this? Well, there is a fact that I haven't told you. The fact is this, that when you have a map, you can, let me tell you in a new slide. Let's go back to tangent vectors, okay? I have a tangent vector here, let's say xp, and I have a map, let's say this is a tangent vector to M, and let's say I have a map from M to N, okay? I'm asking you, using these ingredients, the function from the two manifolds and the tangent vector in a point of the manifold, I would like you to define me a tangent vector in f of p to n. You see what I'm trying to do? I'm trying to transport, using f, this tangent vector from here to here. Of course, if f of p is f of p, then the tangent vector in p will go to the tangent vector into f of p. So let's try this together. As usual, you just have to put together the ingredients in essentially the only way. What is this? Oh, in order to have a tangent vector, what are tangent vectors again? Derivations on maps. So let's call this people, okay? Italian word for whatever. So given a function around f of p, let's call this function g, you have to tell me what is the directional derivative of this function in the point fp. So this one must be a real number, okay, where g is a function, let's say, from a neighborhood of fp to r. Okay, so now the ingredients are a tangent vector here, a map from M to N, and the map from, let's say, from N to R. Put together this ingredient to obtain a number. This is just what I'm asking you. What is this again? A derivative on what? A function on what? We have several domains here. Tangent vectors to M. Yes?
Yeah, derivatives on M.
Exactly. This is a derivative on function of, so it means that if you have a function from M to R, you can take, if you find such a function, you can take the derivative of this function and you obtain a number. That is what you are looking for. So can you tell me, you have a function from M to N and you have a function from N to R. So just the composition. So take g after f, this is a function from M to N to R, and this function you can take its derivative, which is a number, and call this the tangent vector, this way of acting on functions. So you see here g can move, you can take any function, and so you have a derivation on function. Of course, you should prove that this is just a rule. Okay, in order to be a tangent vector, there is a lot of details I'm avoiding the summary, but to be a derivation that must satisfy certain properties, in particular the Leibniz rules and so on. Okay, but it works because this is a derivation. So everything works for this way, and you could prove it in 3 minutes. Okay, and it is useful if you do this when you study with your time. Okay, so what I'm saying is that if I have a map from M to N, then I have an induced map from the tangent space to M to the tangent space to N. You see, in the same direction. So this map is called a push forward. I'm pushing forward. Push forward. I'm pushing forward this map. Well, and out of curiosity, this map is also denoted by df and is called the differential because it's essentially the same things as before. But remember, so that for differential you have 2 meanings: the differential of a function from M to R, differential of a function from M to N, general differentiable manifold. Of course, N can be R. And in this sense, they are the same. And forms are differentials of functions to R. Okay, so this is the differential of a map. In order to avoid this confusion, just think about the induced map, the push forward map given by F. Okay, and in the same way, in a similar way, when you have this map, you also have a map, F star above, which is called the pullback. Why it is called the pullback? Because this takes forms here to forms here. Okay, so vectors can be pushed forward. Forms can be pulled back. Now, look what happens when you try to push forward not a tangent vector, but a vector field. Let's say you have R squared, and you have a vector field on R squared. That means I should take an arrow on every point, right? So, for instance, I could do something like this, okay? And maybe here I can take this. So this is the same over this point, but this is different over this point. And of course, I have other vectors. Okay, this is a vector field filling with arrows all R squared. And imagine I consider the map from R squared to R given by the first components. So the projection, okay, on X1. Okay. Now, this is a vector field. So this is X is a vector field on R squared. This is the notation for vector fields, okay? And my question is, do I have by F, can I induce by pushing forward tangent vectors from here to here? Do I have a vector field that I would call F star of X, a vector field on R? Question. Try doing what we were doing before. That is, take this point and push the tangent vector to a tangent vector here. You obtain, let's say, this. Okay? Well, here it works, but can you spot a problem when I'm trying to define the tangent vector here? What is the problem? That if I push forward this vector, I obtain this. If I push forward this vector, I obtain this. But these are tangent vectors in the same point. A vector field cannot have two values in a single point. So which one is? None of them, of course. It means that I cannot do the push forward of a vector field. This is a very peculiar behavior of pushing forward and pulling back. Because, you know what? When I pull back differential forms, this works. Because when I'm pulling back, what's happening here is the function is not injective. So several points are going to the same point. So P1, P2, P3, going to a point P. If I'm pushing forward in one direction, the different vectors here go to different vectors here, but you have one point. You need just one vector, okay? So pushing forward, of course, it could work. I mean, if the vector field is in some sense invariant with respect to this map, then it would work. This is the notion that Alberto was telling you about last time. That is the notion of vector fields to be F-related. It means that you can push forward in this way. Okay, so you have notion, or maybe if the map is injective, then this doesn't work anymore. Okay, so you can take particular case, but now I'm talking in general. Can you push forward a vector field? No. Can you pull back a vector, a differential one form, a differential form? Yes, because when you pull back a form here, you look for a linear map on a certain tangent space. So you want a linear map here? Well, do what you have to do, that is cook together the ingredients in a way that I haven't told you, but that you can check on the book. It's a very canonical and as usual tautological way, and you obtain a linear map here. You want to pull back the same differential form from the same point to obtain a differential form in another point, pull it back in this way. Okay, this will be related to the differential form here, in the sense that if you push them forward here, if you look at what is there on the point P, there is the same differential form. Okay. I mean, I'm defining an object here. So you see, there is this big difference between tangent vectors and cotangent vectors. That is, despite the fact that tangent vectors and cotangent vectors are essentially the same, they are isomorphic, the fact that in the definition of a function there is this asymmetry rooted in the very definition of the function. The function is a rule that gives for every point no more than 1 point, 1 and 1 point in the image. But you can have in the other direction. I mean, a function must be univoc but not injective. If you ever thought about this, this is an asymmetry in the definition of a function, making a lot of nice things to appear. In differential geometry, this is the reason why forms, cotangent vectors, are much better, I would say, than tangent vectors. Despite the fact that they are isomorphic, this fact that we can pull back differential forms and we can't push forward vector fields gives differential forms a much richer structure, a lot of properties, additional properties on the space of differential forms. That is algebraic structure. I can multiply them, for instance. Have you seen? I can multiply two forms and obtain the wedge product. Okay, I have the Lie bracket on vector fields. I have a product also there. And probably with a lot of work, you can use sometimes these isomorphisms to transfer the structure you have on differential forms to vector fields. But the truth is that when you use this structure on differential forms, they are very natural and very easy to use. Okay, this was a general talk. Anyway, this is the second check. Okay, sometimes to ease your study, I write, you see here, check page 159. So you don't have to look through. I'm too good in this. Okay, you will thank me up later. Now, the differential of a function. We already said everything about this. You see tautological definition already in the introduction. Let's just go through it for 5 seconds, because aim of this course is you become confident that you can understand. So can you understand this formula? Let's say formula definition. You have a function, you have a tangent vector, and you want to obtain a real number because you want a map on tangent vectors. What is this real number? Well, you have a function, you have a derivation on functions. What do you want to do? Just derive the function and you obtain a number. Okay, done. Then, remember that I just told you that there is another notion of differential, the differential of a map between manifolds. Check, do you remember what is this definition? I already told you, and you can find it page 87. So the differential of a map is the derivation given in the way I described it you before. Okay, this question mark was supposed to be an exercise right now, but I will rewrite it here. So this must be a derivation. Okay, we already said it, and we're going too slow. Okay, I don't remember what is this. Just close your eyes. Okay, I remember. Okay, now the exercise is the following. In this sentence, it says that there are two notions of differential. Okay, so if I have a map from M to N, I have a differential. That is what I called the push forward map. And if I have M to R, I have df. Okay, so the same notation for two different meanings. So the question is, when N is equal to R, are these notions related? Okay. And the only thing you should care about is the fact that df is a linear map. Let's go through it here just for one moment, please. Okay, when f is a map from M to N, what is f star of a tangent vector in a point P? I mean, when I say what is, I'm asking for a dimensional argument, not how much it is. Of course, this is general, but in which space does it live? Okay, so in this case, remember, I just told you that f star is going from the tangent space to M to the tangent space to N. So this lives in the tangent space to N. Okay? When this is R, what's happening? Okay, when this is R, okay, When this is R, we know that we have also the differential of f, which is sending vectors to R, not to the tangent space in Fp of R. So you see, cannot be exactly the same, these two notions. So we should relate. So the exercise is, can you guess the statement? Because again, it's a very natural statement. Can you guess how is this number related to this tangent vector to R? Before this, can you tell me one single tangent vector to R? Yes, so as soon as you give me one tangent vector to R, all others are a multiple of that. What is a tangent vector? A derivation. If you tell me one, can be a good answer, but then I will ask you, what is one doing on functions? What do you mean by one? If you have a function on R, can you imagine a derivation, a derivative? Yes, it's called derivative. It's the derivative we learn in the high school. Okay, so in your language, yes, this is generated by one, where one is the in the t, or if you prefer the in the x, it depends of the letter you use for the, and this is of course in a point. Since I'm looking at the tangent space in Fp, this derivative must be evaluated in f of p. Okay. Okay, it's silent mode, but my mother is in the white list of the silent mode. Sorry for this. Maybe she will call again. So now, can you tell me how are this number and this vector related? This is a number. This is a tangent vector that is a vector in a space which is generated, a space of one dimension generated by this vector. So it means that every tangent vector is a multiple of this. So take, this is a number, right? So you can multiply a number times a vector. So you have this vector in f of p, and theorem, this is just f star of vp. Okay, memorize this, and let's check if this is the answer we were looking for. It seems so. It works. Instead of v, we have x, of course. But you see, I mean, it's a game like a Sudoku. We are guessing statements. We are now able to guess statements, to invent theorems in differential geometry. Very often, when you study these things, you see you have ingredients, and you have essentially one way to cook up all the ingredients in order to make everything sense, to make sense to what you're saying. This was my teacher at the university. Maybe I already told you this story, but I will be very short. He was used to say, if there is, in Italian, se c'è giustizia in questo mondo, it works this way. If there is some justice in the world, it works this way. Because we have these ingredients, and they stay together this way. Okay, it's something like when you in the high school, when you have a problem in mathematics, sometimes I was able to find a solution, but not using every data. And so I was telling myself, there is something wrong in the solution because I should use every ingredient. Because we are in the high school, so the teacher is supposed to give me data which I need, not useless data. Of course, in a real problem, this is much more difficult because you have every data. Okay, this is something like this. In the book, when you find a proposition like this, in the proposition you have ingredients, cook up the ingredients in the only way that you can, and often in the book, in the beginning, these ingredients are put up just in one way, sometimes in two ways, but you have to be very unlucky. Okay, so exercise, guess the statement. Next page, I guess what I told you was in the next page. Okay, and in the beginning, look here, you already know this. These are isomorphic, but not canonically, because the isomorphism is not unique. If I write my isomorphism here and Roberto write his isomorphism there, we are probably having two completely different isomorphisms. But if we look for an isomorphism from these two spaces, we can find one which is completely canonical. So there is just one, and that is. Okay, so let's have a look. This is the next page. We already said everything here. So let's go on. I already told you that every one form is a linear combination of these differentials. Remember what are the differentials? The basis for the cotangent space. And what is this xi? Semantically, what is its meaning? It's a? Yes, that is a? It's a function, okay? Because the acts on function. You do the differential of functions, okay? And this is a very simple function. Perfect. So it means that when you have a basis, you have coefficients, and when the point is moving, these coefficients, which are real numbers, moves with the point, so they become functions by themselves, okay? And this means that you can again differentiate this one form by taking derivatives of these functions. And so on, you have a 2 form, and then a 3 form, and then a 4 form, and so on.
Well, a form is simply a high-level derivative.
A K form is obtained by high-level derivatives. I wouldn't say is a high-level derivative. Derivatives are tangent vectors, not cotangent vectors. So a derivative is the tangent vector. Okay, in some sense, a form, let's say the differential of a form, the differential of a function is sum of its partial derivatives. Okay, you know this formula, right? Probably the total differential formula. This means that the coefficients are computed by deriving, acting by derivations on the coefficients of the standard basis. Okay.
Yeah, it's a near combination.
Okay. So in some sense, the differential is related both to tangent vectors and two cotangent vectors. Okay, then we can take the union. You see, we are going a little bit faster than usual because we are just saying again the same things. Okay, this is the cotangent bundle here. We glue together all the cotangent space, and you guess what? You can do the bundle of two forms. This is the bundle of one forms. You can glue together all the vector space of two forms. Okay, you can glue together the sum of the vector space of one form with two forms. Okay, you can glue together the sum of every form, one form, two form, three form, four forms, and so on. And you obtain the bundle of differential forms. No more differential three forms, differential four forms, differential one forms, differential forms. Okay. And there is a lot of technical thing to prove that everything works. Okay. And then there is this characterization of C-infinity one form. Up to now, I was completely ignoring the fact that we are concerned with C-infinity maps and so on. Well, whenever I was saying, and this is a function, and this coefficient is a number, but now we move the point, it becomes a function, there is the additional requirement that must be a C-infinity function. We are doing C-infinity differential geometry. Okay, so everything is C-infinity. These are the technical details that make the book long 500 pages and not 50 pages. Okay, because there are a lot of things to say and to consider. And just to understand the problem, I told you that, for instance, a differential one form is a section of the cotangent bundle. That means this, okay, is a map in this way, which is a section. That means on P there is a cotangent vector on P, okay. And of course, in order to be this a differential form, that means a C-infinity form, this map omega must be C-infinity. But C-infinity, what does it mean? Well, this is a manifold. Remember, I told you this is also a manifold. Here we need the fact that this is a manifold because this map is C-infinity as a map between manifolds. Must be C-infinity from M to T star of M. Okay? But you also know that this omega can be locally described as the sum on the dimension of the manifold of coefficients AI, coefficients which are functions. If this is P, this is a function of P. This is the, well, in this notation, maybe it's better if you write omega of P, okay, because this is a function on M, and times the basis in the of the cotangent bundle, which are the xi in the point P. Okay, and remember this xi exists only locally. We don't have global coordinates on M, but we are in a small neighborhood, and this set is a manifold. Remember, a manifold is something which is locally exactly like Rn, and so we have xi. Well, we could say now that omega is C-infinity. It would be reasonable to tell that this is C-infinity if AI are C-infinity. As maps from, these are maps from U, the local set around P contained in M, to R. It would be nice, right? But so we have to decide which one of the definition. Which one would you choose? The form is C-infinity if it is C-infinity in this way, or we say it is smooth C-infinity if it is C-infinity in this way. which one would you prefer?
I prefer the second.
You prefer?
The second one.
The second one.
But I think that there may be some condition which we can extend it to the first one, because the positional manifold can be locally Rn.
Well, these are manifolds, so this is a well-defined notion, okay? To be C infinity has a meaning, okay, because these are manifolds. So my question is, which one do you prefer? And you said, I prefer this one. You know why you prefer this one? Because you know what is to be C infinity for function on values on R. And you feel less confident on this notion. Well, but the point is, do you have to choose really?
No, in fact,
It's exactly the same. But as you can guess, this is a theorem. So, section 17.4, characterization of C infinity one form, is a section devoted to prove this fact. Okay, and in particular, see lemma and proposition. Look at this proposition, it's very funny. Proposition, let omega be a one form on a manifold. I'm not saying it is a C infinity one form, okay? Then the following statements are equivalent. The one form is smooth. The definition of smooth here is as a map from M to T star M, okay? Smooth in this sense. Second, the manifold has one atlas such that if you take any chart of the atlas, the coefficients relative to the frame dxi in that atlas, you recognize what I was saying before, are all smooth. Look, the 2 states that there is one atlas. Now there is a problem. Roberto arrives and he chooses another atlas because he's a guastafeste and they always want to do something different from the others. And maybe in the other atlas, the coefficients are not smooth. Do you agree this would be a problem? Theorem 3, this is not possible. On any chart on the manifold, whatever atlas you choose, as soon as it is a compatible atlas, of course, on the manifold, this cannot happen. The coefficients are always smooth. So, you know what? Your definition, the definition you like, is fine, and it is exactly the global definition. Everything works, and you wonder why? Remember the point? Transitions on the intersections, the manifold, that maps are C infinity. And if you compose, at the end, if you try to prove this, at the end of the computation, there is the fact that the composition of smooth functions is smooth. Okay? So, for instance, can you answer this question? Why is the differential of a C infinity function again C infinity as a one form? Hint, total differential formula. If f is C infinity, what are the coefficients of the f? The partial derivatives, which are C infinity by definition of C infinity of f. So the coefficients of the f are C infinity. So theorem, C infinity as a one form. Okay? Okay, a lot of things. You see here, no annotations means just skip it. Be careful, when I say skip it, means in order to understand the things, you don't need it. But of course, these are proofs. These are some technical detail that if you have time to do everything in detail, of course, it is not bad. I mean, in the first reading, you can skip if you want. But if you want to try something, trying giving this proof can be a nice exercise, very useful exercise. Okay, then you know what? Have you ever heard of the fact that one forms can be pulled back? Remember what this means. Again, we have a map from manifolds. Then you have a push forward in this direction. You see tangent vectors go to tangent vectors. Well, you can take the dual of this map, and so you go in the other direction, and cotangent vectors becomes cotangent vectors, but in the other direction, okay? So one is the push forward, the other is the pull back. The pull back is called, you usually put the word, the prefix co, means co-vector, co-differential, means that you go in the other direction. You take the dual, okay? Co means usually take the dual. And all of this reverses the arrow and pulls back a covector. Another notation for the differential is F star. We already say this, okay? And if we want to check how this is defined, this is the definition. We will go through this after the break. I now want to go to the end of this chapter. Okay, now you see, well, details. Now we have defined the pullback of one forms. So I can pull back a C infinity one form, right? Is this still C infinity? Well, if there is some justice in the word, yes, it must be. Otherwise, when we take the pullback, we have to add the hypothesis and assume that the pullback is infinity. Come on. Well, is this pullback C infinity? Yes, answer. But to answer this question, we first need blah, blah, blah. So it means that it's not at all something very trivial, okay? You need a lot to say before. Details, technical details, important details. But you must become confident that you can study this. You don't have to go through the details right now. Okay, also because it's almost coffee time. And okay, these important properties. Let me. Okay. My computer is tired. Okay, this is a part. Okay, this is important. I think we can stop here. What's the time now? Okay, so I would take a break here so we can start fresh with the notion of immersion embedding and so on, which is important. Okay, welcome back. Please give me a tell me if you can see my screen and if you can hear my voice.
Yes, both.
Yes, everything.
Thank you. So let's start again and let's go on through all these notions. So up to this moment, we have given so many definitions and different notions and concepts. And now there is something I want to tell you about these different notions we are giving. That is this sentence. We need to establish 3 commutation properties of the pullback. So we have the notion of pullback. That means I can pull back differential forms. And I can also differentiate differential forms. I can also sum differential forms, and I have also the wedge product of differential forms. Meaning, if omega and tau are differential forms on a certain manifold M. When I want to say that these are differential forms and I don't care about the degree of these differential forms, I put a star here. It means these are differential forms or whatever degree. They can also be a mixture, the sum of a 2 form with a 3 form and something like this, okay? But just think about 2 forms in any degree. What I'm saying is that if I have a map from this manifold to another manifold, then I have the pullback of omega. Since this is the pullback, I need differential forms here on the other manifold. Okay, I have the pullback of omega, I have the pullback of tau, and these are differential forms on M. But you know that when I have differential forms, I have also I can sum them, I can multiply them. Okay, I can take the exterior derivative of them. So this is a differential form again on N. This is a differential form on N of degree, the sum of the 2 degrees. Okay, and this is again a differential form on N of degree 1 more the degree of omega. And so you could ask, what happens when I take the pullback of this? What happens when I do F star of omega plus tau? What happens when I take the pullback of omega wedge tau? And what happens when I take the pullback of the differential of omega? Okay, you see, all these kind of questions are also very natural. And I'm telling you this, not because I'm particularly interested in these 3 properties, which are very natural, but because of the general argument we have, because of the general argument we have in differential geometry, that is, when we have several notions intertwined with each other, we ask for them to be compatible, or we ask whether they are compatible in some sense. And for instance, here, to be compatible, I mean, it is reasonable to expect that this is, what would you expect for this? The sum of the pullback. Okay? I mean, if this is not happening, then I would say that there is something ill-behaving with the notion of pullback and the sum of differential form. And in fact, this happens. And the same here, you obtain the wedge of the to pull back, and the same here. This is actually very important, and it's not apparent. I mean, this is sort of linearity. It's very, very easy. This is just the fact that everything is defined point-wise, but this is not obvious. Okay, but it works. Observe that this differential is different from this, because this is acting on forms on M, and this is acting on forms on N. Okay, and so on. These are the 3 properties that here is saying we need to establish these 3 properties. And the first of these 3 properties is this one. You see? So proposition, not theorem, because it's very easy. Just a proposition. But I mean, it's not one line. It's several lines of computation. Very, very easy computation. Okay, this book is very gives a lot of details. This is actually a one-line computation if you do it in a more concise way. But just to let you know, to let you understand that these are the details we are concerned with when we are doing differential geometry. And these are the other 2 properties. Now, Okay, you have also this property with respect to the multiplication by a function. Okay, so there is a sort of linearity with respect to smooth functions. Now, all of these properties summarize in notion of compatible structures. What is the structure related to the sum and to the multiplication with functions? In an algebraic language, we say that differential forms have a structure of a C-infinity module. When you can multiply by a function, when you can multiply by a real number, you say you have a vector space, right? If you have the sum. When you can multiply for elements not of a field, but of a ring, if you know the difference, I mean, functions are worse than real numbers because they are not always invertible. Okay, they have not an inverse. So we say that the structure is a structure of a module. In this case, a module over the C-infinity function. Well, what we are saying here, in some sense, is that this map is an homomorphism between these kind of structures. Okay, and so you can remember in the compatibility in this way, just remembering that structures are compatible, that the pullback is an homomorphism of the structure, and that is compatible with the differential. This is an additional property, and so on. Okay. Now, we have the following argument, the following topic. We want to check what happens when we have an immersed submanifold, when we have a manifold which is contained in another manifold. Okay, and this topic by itself, not the restriction, which is this part, okay, that we will see later, but this topic by itself, the immersed submanifold, what does this mean? It's interesting and important by itself. It was in the first lecture, again, and we are having a sum up, a summary of these notions that we had in the first lecture. Here again, check means check whether you remember, you understand, you know what are submanifold, what means immersed submanifold, okay? Let's go to the next page. And as you can see, in the next page, I have pasted, this is part of the same annotated book, and it is at page 115. And here they say what are immersions. Okay, they say actually what are submersions and what are immersions. And the notion, the important notion that Alberto was talking about in the last lecture also is the fact that the differential, you know, there is the Taylor formula, right? And you know the derivative is expressing the behavior of the function at the first order. In the same sense, now that you know the differential is some sort of more high-level language, but it's still the same. It is expressing the behavior of your function in a point, around the point. So it makes sense to look at the differential. Okay, the differential is a linear map, and to ask whether this differential is what is it doing between these vector spaces. Okay, so if we have a map from a manifold to another manifold, we have the differential in a point P that is a map from the tangent space to M to the tangent space to N. This is a linear map, okay? If you want to say that this linear map is well behaved, what would you ask for a linear map in general? If you want that the map is good, or the opposite when you say that a linear map is bad? Well, this can have dimension 10 and this dimension 7, so cannot be invertible in the. I'm sure if I tell you instead of a map, I give you the matrix. So this is 10 by 7 matrix. You look at the rank. If the rank is not maximal, you cannot say the rank 0, not the determinant, because determinant is just for square matrix. But in this case, the rank, if it is not maximal, then this map is bad. What does it mean, maximal rank, in this case? 7, that is surjective. But what if we have 7 here and 10 here? The maximal rank is still 7, but means injective. You see, so depending on which one of the two dimensions is bigger, maximal rank means something which is completely the opposite. In both cases, you say, okay, this map is well behaving, because in some sense, it is not collapsing more than she must. I mean, from 7 to 10 dimensions, of course, there are, not here, from 10 to 7 dimensions, of course, you have to collapse at least 3 dimensions. But if you collapse 9 dimensions, then you're bad, okay? Well, so there is this notion, maximal rank. So we look at the rank of the differential of a map in a point, and according to whether the rank is maximal or not, we say that the map is some kind of map or not. In particular, we are interested in the case where F has maximal rank, and we are interested in the special case where the dimension of the domain is less or equal to the dimension of the codomain, so that the map, the differential, is injective. Okay, in this case, we say that the function is an immersion at P. So immersion means, in that point, that the differential is injective. And dually, a submersion means that the differential is surjective. But in this moment, we are interested only with immersions, okay? Now, by immersed submanifold, we mean at least a map F from N to M where the differential is an immersion at every point, okay? If F is an immersion for every point. This is the minimal requirement to tell that map is an immersed submanifold. But be careful, because this is a very weak terminology. This is not shared by everybody for the reason I'm showing you in this very same slide, because it can happen that the differential is injective in every point, but the map is not even injective. You see the difference? We have the map, which is not a linear map. The map is from 2 differentiable manifolds. And we have the differentials at every point. These are linear maps. We are requiring for these differentials to be injective. Okay? And this means that locally, this is the inverse function theorem, this means that locally this map is invertible. Okay, but what does it mean locally must be specified? In particular, this can happen. Let's have a look in a qualitative way, in a global way. I'm mapping the open interval from A to B in this way in R square. This is the image of this open interval. Without making computation, you could write the equation and you could make actually the computation, and there is the computation somewhere in the book. It is an exercise. But do you agree that, sorry, do you agree that the tangent space here is mapped to the tangent space here? That means the differential in that point is injective. The tangent space here, on the other side, is mapped to the tangent space here. You see, because this is a curve, we're just moving this way. So the tangent vector, it depends on the time we are looking at. Okay? But you see, the map is not injective. So if I call it a submanifold, I would expect this to be a manifold. I mean, you call it a submanifold, it should be a manifold, right? So let's ask, can this be a manifold? This set? I mean, if I take point close to this, let's say this set, if I take this kind of cross, can this be homeomorphic to R or to R squared? Well, to R squared, not surely. To R? Well, you have to think about it, but there are several reasons why this cannot be homeomorphic to any open subset of R. One of these reasons is that if you remove this point, you obtain 4 connected components. Well, there are no open sets in R. Theorem, you should prove it. There are no connected open sets in R because the original one is connected. That when you remove a point, you obtain 4 connected components. You know what? Connected open sets in R are open intervals. So just remove a point from an interval, you obtain 2 components, not 4. So, but you can prove this in several different ways. It's not easy, it's a topological question, but this means that this cannot be a manifold. Okay? You see that in saying this, I'm assuming that the open set of this set is obtained as intersection of an open set of R squared. So I'm implicitly thinking to this object, this set, as having a topology induced in some way from R squared, meaning that the open set here is obtained by intersection with open sets in R squared. Okay, this is not really necessary, as the following example shows. I told you that the map can be an immersion, okay, differential injective in every point, but the map can be not injective. That's the worst case. In that case, the set is not even a manifold, okay? So it is called sometimes immersed submanifold, but it is not even a manifold. So better not call that submanifold, okay? Next step is that F is injective by itself. So injective plus the differential is injective in every point. Okay. Now, a very important question is, now that this is a manifold. In this case, the image F of n is a manifold, but can be a manifold in 2 different ways. Maybe more actually, but we are interested in the natural ways that are. As usual, this is the open interval is n, and this is going m, which is R squared. Okay, and the map is such that, let's say, let's do something like this. Okay, this map is injective. Okay, injective means that we are not touching back. This map is injective, and I can give to this subset, this is f of n, I can give two topologies on it. Which one? Well, one is the one we were talking before about. Take open sets in M and tell that the open sets in this image are the intersection. So this is open, and this is open because it's an intersection, and so on. These are all the open sets of your group. Of course, you can have also, this is an open set in R squared, so this is an open set that you can easily prove it is the union of two connected open sets, okay? And this is one topology. So this is a space in some sense, and you can prove that there are charts, local charts, and this is a manifold in this sense. But there is another notion of another a priori different topology on this subset. That is, take a set here and declare it to be open when its pre-image here is open. Okay, so declare it, the open sets here are just the open sets here. If now I ask you, so I'm giving you f of n as a set with one topology, topology 1 induced by R squared, and then I have given you on f of n a topology 2, let's say induced by n using f, using the map, okay? Which one of the two is, in your opinion, homeomorphic to n? Surely. Homeomorphic means that the map is invertible on its image and continuous. Homeomorphic to this one or this one? The second, you can see it's more, I mean, the second is tautologically homeomorphic, because open sets in the seconds are nothing more just a rephrase of open sets in N. I mean, we are using F to look at these subsets with the topology, okay? So they are homeomorphic, and so this is a manifold, because if this is a manifold, everything you just read through F. Now, the point is that sometimes, and in this case is, also this one is homeomorphic to N. That means that happens when the two topologies are the same. If you think nothing bad can happen in this picture, the topologies are exactly the same. So you could be tempted to say that when F is injective and the differential is maximal rank in every point, then this is happening. The two topologies coincide. Not true. And we have this example. Maybe we can look here. Look at this example. What's happening here is that the point B is touching the point P, but not really touching, because otherwise it would be not injective. But it's, you can parameterize this open interval in such a way that this point is going to this. So What are the open sets around P? Still as before. Not really a cross, but just a cross with 3 components when you remove P. You see, something we would call this pathological is happening, something bad behavior. This is an example of a manifold which is, this is a manifold, but only in one of the 2 senses. This is a manifold with the topology induced by the open interval. Because it is injective, okay? There is not a point, B is not f of B, is not f of P, because B is not included in the domain. Okay, this is the point, that everything is open. So this is injective, but nevertheless, the 2 topologies are completely different. With the induced topology from the ambient space, this is not a manifold. With the first one, it is a manifold. And you know what? When we want to talk about submanifold, we are interested in submanifold. This is just a manifold. It's not a submanifold. I mean, it's a manifold by itself that I have put in R square, which is a manifold by itself. In the previous language, these 2 manifold structures are not compatible. They don't talk to each other, okay? Well, in the language, anyway, this is an interesting object. This is called the immersed submanifold. And in order to distinguish it from the other example, when the 2 topologies coincide, we have in English 2 different words for these situations. In the first case, I say immersed submanifold. In the second case, I say embedded submanifold. Both these words translate to sottovarietà immersa in Italian language, and this creates some misunderstanding. So in Italian you would say this is a varietà immersa nel senso embedded. You would use in the Italian language the English word. To overcome this terminology problem, you can say regular submanifold. Okay, that is also very nice. It means it is regular. It's not so ugly as this. Okay, and so what I'm saying that we are interested in the third case when F is injective and the 2 topologies coincide. Well, we are interested also in the previous case, in some case. In this case, you say that the manifold is regular. The map is called embedding, and for this reason, the image of this map is called also an embedded submanifold. Okay, so in this sense, embedded submanifold is the image of an embedding. A regular submanifold is a priori something different. It's something such that locally can be expressed by coordinates in this way. Is an hyperplane. When you look in coordinates, a regular submanifold, there are some charts such that in that chart, in that open set, your submanifold is just given by some coordinates equal to 0. So this is a picture in R square. This is a regular submanifold of dimension 1. It means that there is a chart here where the part of submanifold in this chart, that is this part you are seeing here, is just given by the second coordinate equal to 0. Okay, we call this an adapted chart, and when you make computations on submanifolds, this is very useful because I mean you can take coordinates that are very nice, that are compatible. You see, the use of the word compatible in the mathematical language is very vast. You can use it in several different directions. In this sense, we would say that this chart is compatible with the relation between the submanifold and the manifold. Okay, well, so we have 3 notions. The ugly one, differential injective, but the map is not injective. Forget it. bad. The intermediate one, the differential is injective, the map is injective, but the two topologies are not necessarily the same. Well, the fact that the map is injective actually is enough, also in the first case, now that I think about it, is enough to tell things about differential forms, which are defined on the tangent space. And this is why we are talking about this. So let's go back to the beginning, that is this part. So we are here now, okay? We made this check. Now, when the differential is injective, it means that the tangent space to S, here is called S, the immersive manifold, is contained. Injective map means that I can take this tangent space and I can look at it as it is contained in this other tangent space. Okay? This means that if I have a differential form here, this is a map on the tangent space, right? Linear map on the tangent space in a point. So I can restrict this linear map to this subspace, this subvector space. And this is called the restriction of the differential form. But be careful, there are two restrictions involved here. Can you see them? So I have omega from M to the tangent space, the cotangent space of M. This is a differential form, a one form. Okay? Now, if I want a differential form on S, what should I have? Well, first I have to restrict from M to S. And so I need to have a map from here to here. Okay? So I need, in some sense, that this is contained here first. After that, then I have to define what is omega restricted to S when evaluated on a tangent vector to a point S, point here. Because this is a linear map on the tangent space to S. And since I want to say that this is omega of this tangent vector, I need this tangent vector to stay in the tangent space to M. And this is where the immersion part enters, where the fact that the differential is injective, because these tangent vectors, I can act by the oh, yes, I have a map here. Okay, this is the immersion. Let's say, let's call it I, the inclusion. Okay, you see the point. I can see from your face that I'm not clear here. For a mathematician, saying that S is contained in M and that there is a map I from S to M, I injective, are two different things. I mean, also for you, I guess. This is a subset. This is a completely different set which can be included by this rule into M. Okay, and now we are discussing what happens in this case. So I have a differential form here, and I can take the pullback of this differential form, which is a differential form on S. And I'm telling you what is this pullback. Well, this pullback is just described in this way. If you think to tangent vectors as tangent vectors to M, you are just evaluating your form on this tangent vector, but this tangent vector lives here in M. Okay, and so what I'm saying is that you can write this way or just omega restricted to S as soon as you have an immersion. Okay, pretty sure I was not clear, but anyway, here you have everything you need to understand. Let's check. Okay, maybe we can make an example. Okay, what do you think about it? Would be nice. Well, the example is on S1, the circle, as embedded as a subset, as a submanifold in R square. What is this embedding? Well, the map is the following. Okay, the circle is parameterized this way in R square, okay? And I can take what we would call the velocity vector field. This is the curve. The velocity of the curve is just the derivative in the standard sense, okay? Now, what I want to do is to give a meaning to this. I mean, when you say that the derivative is minus sin t and cosine t, because you are just taking derivatives of these two functions, what do you mean? Well, you can observe that this derivative with respect to x and y is written this way. What do you mean? This is a velocity vector. You see, it seems a point in R square, but it is not a point in R square. Because you remember, the derivative, what is? Let's remember in this sense. This is the map from R to R square, sending t to cos and sin t. Okay. Now, I'm writing the derivative c prime of t. Can you tell me what is this derivative in our new language, new, more complicated language? This is a map. And these are manifolds, okay? Think about M and N. When you have a map from M to N, forget about R and R square. What can you do with these maps? Exactly. You remember how is this map denoted and called? But the map is denoted by C star, or also the differential of C, but let's say C star, and it goes from the tangent bundle of M, no, wait, it goes from the tangent space in a point P of M, but let's call this point T and not P, because it is here, okay? So you see, it goes from the tangent space to a point T to the tangent space to a point CT. And what happens is that this tangent space in T is the tangent space to R, which is R, which is obfuscating the real meaning of this. Exactly, and this is the tangent space to C of T, which is x, y, which is as an image of this map given by this, okay, to R square. Again, tangent vectors to R square are still given by two real numbers, obfuscating the meaning. Meaning that this map for you in the original language was just a map from R to R square. But you see, you are losing a lot of information in writing this. You are losing the fact that you have tangent vectors in T and tangent vectors in C of T. And now the fact that this derivative is minus yx, that is written in this way, this is exactly, yes, is there a question? Okay. This means exactly that this is the image of a tangent vector. Which tangent vector? Do you remember? C prime is exactly the coefficients you are multiplying the standard vector here, d in the T. Remember that theorem. Well, that was another part actually. So I'm saying that, so this C prime is just the image of this vector, okay, on which is the tangent vector on R, in the point T, a notation which is overlapping. I mean, this is different from this. This T is the coordinate on R. This is the point that you are considering. So maybe we can take the derivative in T0, and so you obtain the point cosine T0, sin T0, and this point on the circle means that if you are starting from T0, which is corresponding to this point, let's call it x0, y0, then the image of this tangent vector, canonical tangent vector, the only tangent vector essentially you have on R in every point, this tangent vector to T0 is mapped to a tangent vector to this, a tangent vector into R square, which is tangent to the image of this map, of course, which is given by minus y s0, which is this tangent vector. Okay, so this is just, if you want, C star in T0 of D in the T in T0. I know that sounds very uselessly complicated, but just to understand what we are doing, okay, to give a meaning. Of course, you can just say this, but the important part that you are able to understand that behind the scenes there is all this language, all this terminology, and so on. Because sometimes you need this to make computations in more complicated setup. Okay, now that we have this vector field, this is the exercise, let's say, the question. They ask to find the one form on S1, which is on this vector field 1. So let's take a big picture. This is S1. This is the point x0, y0. This is the tangent vector, which is minus y0, x0. And we are asking a differential form on S1. If you call this x, this vector field x, which is a tangent vector field to S1. S1 is the symbol we use for the circle. Then I want a differential form omega such that omega of x in every point is equal to 1. Okay, so first, what I'm looking for, I'm looking for the dual basis to this. Do you agree this is a basis for the tangent space to the circle in every point? Because the tangent space to the circle, this is a one-dimensional manifold, has dimension 1, and so it is generated by any non-zero vector. If I have a vector field which is everywhere non-zero, and it is everywhere non-zero because this is the form in coordinates of R squared, and so I'm looking for the dual basis. Okay, how would you find such a one form? This is a linear map here. Well, here we are in R square. We are using the fact that we are a submanifold of R square. So we have in R square, we have the x and the y. This is a basis, okay? And this means that on S1, we have the x restricted to S1, the y restricted to S1. Okay, this is why before I was telling you what does it mean to restrict one form, okay? So let's avoid this cumbersome notation for the moment and just ask for, since any differential form on R square is a combination of these, we have a differential form will be a combination of the x and the y with some coefficients. Of course, these coefficients are functions when the point is moving, and we want these coefficients to be function here on the circle, and we want this form to be 1 on x, but x we already computed it. X is minus y. X, what does it mean in terms of tangent vectors, in terms of derivations? Means that this is minus y d in the x plus x d in the y. You see why this is useful? So now we have just to compute a dx plus b dy, where these are, we don't know how much and we want to find them, on minus y d in the x plus, but I need another d in the y. Let me check. So a dx over this so the x of d in the x is 0. So this is 0. No, it's 1, sorry. Okay. Minus ay. This is 0. This is 0. And this is plus bx. And we want this to be 1, right? Can you guess a and b function on S1? If minus a is equal to y and b is equal to x, you have just the equation of S1. Okay, so we just proved that y dx minus y dx, is this correct, plus x dy is such one form. Let me check. Yes, it seems so. This one. Okay. So this is one such form. Why one and not a unique solution? Because of course any multiple of this will work. Not really. Not multiples. No more one on that. Okay. Anyway, this is one such form, and this is a nowhere vanishing differential form on the circle. Okay, so in some sense, this one form is generating the cotangent bundle in the same way as this vector field is generating the tangent bundle. If you remember from the last lecture on Lie groups have the particular property that the tangent bundle, in particular the tangent space on the identity, is generated by certain vector fields, which are given by the multiplication by certain element, and the cotangent bundle of a Lie group is of this form, as global differential one form that span it in every point. We say that it is parallelizable. And I think Alberto told you this, that spheres are parallelizable only in 3 cases: dimension 1, dimension 3, and dimension 7. Okay, every other sphere is not parallelizable, meaning that on the sphere of dimension 1, you have a never vanishing vector field, this one. On the sphere of dimension 3, you have 3 never vanishing vector fields. Okay, on the sphere of dimension 7, you have 7 never vanishing vector fields, but on every other sphere, the number of never vanishing vector fields is always less than the dimension of the sphere. Okay, in some cases it is actually 0 on every even dimensional sphere. All these things that I'm telling you cover a whole complete other course in topology or something like this. Okay, to prove these statements, we would need a lot of things. Just to tell you something nice and funny about what you do with this kind of things. Okay, this is a thing that I pointed out here. When I have S1 contained by the inclusion in R square, I have the coordinate in R square x1 and x2, x1 or x and y as you want to call them. And this is a function on R square, right? So you can pull back and you have this function x1 pulled back as a function on S1. Okay, in the same way, you can push forward tangent vectors. So since here you have coordinates given by x1 that we can call x1 bar, you have the derivative with respect to x bar on the circle. You can push forward this derivative, and you would expect, if there is some justice, to obtain this, but no, you don't obtain this. You obtain something different. This is computation you can do. The fact is that when you are pushing forward this tangent vector, if you want to obtain this means, I mean, you are pushing forward through the immersion, so it should be this, right? And you should obtain something which is still tangent to the sphere, which is not. This is not tangent to the sphere. Okay, so this can be a problem and source of confusion when you do computation, because you have the derivative with respect to a coordinate, and in some computation you can be tempted to assume this is just the in the x, but from this picture it is clearly not. It is in certain points, for instance here. they coincide, but not on the other points. Okay. Okay, there are problems, but okay, let's go through chapter 18. Differential K forms. We already know everything. We have K covectors. I mean, we already did it in Rn. We have K covectors in Rn. That means that we have K forms on the tangent space in a point. And this means that we can take the union of K forms, and from this union we can take sections, the same as before. And this is a differential form, a differential K form. Let me check what is in the next page. Okay, this is a mess. We're not going through this, but this is just a summary of important part of the section on forms on a vector space. Okay, remember the technical part, multilinear function. What is a form? You remember from the beginning? A form is, I repeat for you, a multilinear function on a vector space, on the tangent space in a point, which is not only multilinear, but also alternating. Okay, so we are interested in multilinear function, and this is why on the book we have a section on multilinear functions, and we say what is a multilinear function. So you see already the definition of multilinear is sort of complicated, because I have to put dots here and state that this holds for every slot of the function, because I mean multilinear means this, linear in every slot. And then, since I'm interested in alternating functions, the technical language to say when a function is alternating must take in account if I'm swapping the arguments in an odd or even way. I mean, if I'm swapping 1 with 2, then the sign of this permutation is -1. But if I'm swapping 1, 2, 3, putting 1 over 2, and then again over 3, obtaining 2, 3, 1, this permutation has not changed the order of 1, 2, 3. It's evident, it's just 2, 3, 1. You are just starting from 2, okay? But it's the same way of counting. And in this case, I'm not really alternating. So the sign in this case, swapping the arguments in this way, is plus, not minus. And this takes you to the language of symmetric functions and alternating function with the, look here, the sign of a permutation. Can you understand that this is making everything from the technical point of view a little bit more complicated? But it is easy, but it is necessary. I mean, you cannot avoid this if you want to prove statements, okay? But the idea behind that is always the same. And well, here I told you why multilinear maps are important. I already told you before the scalar product is a symmetric multilinear bilinear form, and I forgot an example of alternating form, very important. The determinant is alternating. Never wonder why swapping columns or rows, the sign is changing, because the determinant is a multilinear function on a vector space, which is also alternating. The determinant is the prototype of the maximal degree differential form in a manifold. Okay, and then the notion of tensor product, we already said this, but you see, I told you just by chatting what is the tensor product of two multilinear maps. I say just the product, but if you want to define this, you add this notation in general, which is a k plus L linear function and so on. But it is just the product, okay? This is the element-wise product. This is the product between two numbers, okay? Not the scalar product or something fancy, just the product of two numbers. And this means that on a manifold, for instance, on R squared, look at this expression. What is this expression meaning? This is a multilinear map, bilinear actually. It is not alternating, because you can check that if you swap the argument here, you don't obtain the same, because there is not the wedge product, essentially. And this map means, for instance, this part, what is doing? If you have a vector tangent to R squared of coordinates 3, 4, what is dx1 tensor dx1 doing? dx1 means just take the first component. You see, because this 3, 4 is actually 3d in the x plus 4d in the y. And dx, sorry, d index 1 plus 4 d index 2. And dx1 is just taking this and sending it to 1. So dx1, this tangent vector, is just taking 3 square. And dx1 tensor dx2 is just taking 3 times 4. And so in this way, I'm just describing a bilinear form on the tangent space to R squared. And this is the way you can describe a metric on the tangent space, because a scalar product is a bilinear form, symmetric actually. So I think this sentence is a mistake. I will correct it. Okay, anyway, this is some notation that we will use in the next lecture to describe metrics. A metric will be given locally by dxi tensor dxj with some coefficient and the sum over I and j. And this is a notation that I'm telling you because it is very likely that you already met a similar notation. Okay. Here there is the notion of wedge product. Okay. Okay, this example, also this we already talked about, but let's restate in this way. Now we have a coordinate chart on a manifold. That means a coordinate chart, remember, means we have x1, x2, xn. And means that here we can take the partial derivatives in that directions. These partial derivatives are a basis for the tangent space. Do you have a déjà vu? I hope. Okay. And as we have already seen here in proposition 17.3, there is a dual basis to this basis. Dual basis means a basis of the cotangent space. This dual basis is given by these differentials that, remember, are just the differential of these functions, because x1 is a function, is the projection on the first coordinate, and so on. And since this is a basis, it means that this one, also when P varies on the open set, this one are a basis for the tangent bundle of forms in that chart. And this means that when I take the wedge product of some of them, I obtain a K form. If I take the wedge product of K of them. And you see now a technicality. I don't want to take the wedge product of the first k or of the last k. I want a way to denote the wedge product of the second times the third times the fifth times the last. Okay, so I have to use sub-indexes in the set from 1 to n. Okay, so a K form is this very, very ugly notation. A I1 IK times dxi1 wedge dxik. Okay, it's I mean, not ugly, it's just heavy. We cannot avoid it, but actually we can use the notation called multi-index. We can say, okay, let's call by definition I is this set A1 AK. And so this notation is just the sum of a multi-index omega dx multi-index. Okay, but just a shortcut, a notation, but just to show you which kind, you see this one, which kind of problems you can encounter when you need to formalize everything. Okay, and this is the set of multi-indexes of length k on a set of length n. Okay, and since if you take dx1 wedge dx3, this is of course a two form, but it is essentially the same as dx3 wedge dx1, meaning that it is the opposite. So if in the base you put this, you shouldn't put this. This means that when you take element of a basis, your multi-index must take care of the fact that the indexes must be increasing, must be ordered in a fixed way. Okay? Yes, there is a question? Okay. You know what? Local expression for a K form. Well, since this is a basis, locally you have coefficients. In the particular case, this is important for the last slide. In the particular case, when your K form is obtained as the differential of single one form, which are given as an exact differential, as a differential of a function, then you can guess. I mean, remember that the differential of f is the partial derivative of f dxi. Okay, when you take the differential of f wedge the differential of g, you will have some multiplication of the partial derivative of f and partial derivatives of g. Okay, when you take this differential, you will have partial derivatives of every function. And if you take f1, fk, which are functions from m to r, all together, they give you a function from m to rk. Let's say this m is an n-dimensional manifold. You obtain a map from Rn to Rk. And the function I'm telling you about here are the partial derivatives of the single component. So all together, what happens is that they form the Jacobian determinant of the transformation given by this map. So the wedge product, in this sense, is expressed locally by the partial derivatives of this function, put all together in some way that they form the determinant of the Jacobian matrix. we shouldn't be surprised from this, because the wedge product is just alternating its coefficients. And what is the determinant doing? It's just alternating. Okay? So I wrote here reasonable, because the differential contains the partial derivatives and the wedge product is alternating. Okay. In particular, for top forms, look at this. What happens? For top forms, you have a map from Rn to Rn, so the Jacobian is squared. You can take the determinant, and this is the relation between this n form and the standard n form of the basis. And this is the transformation rule that is needed for integrals to work. Okay, the bundle point of view. You can see I didn't put the yellow marker here because it's already, everything is just said. We take the union. You see, I mean, it sounds complicated, but now it shouldn't be as much complicated as it was in the beginning. I'm taking the union over all the point of this. What is this? Oh my God. Well, we know it is the alternating functions on k copies of the tangent space in the point P. Okay, is the wedge product of the cotangent space. Means that I take single elements here, which are one form, and I take the wedge product of them. And for what we have said, these are exactly the K form, okay? The K multilinear alternating maps on the tangent space. Then we give it a topology here, and we make it a manifold, okay? And then we take sections, and congratulations, you have K forms. You see, this is the notation I'm using already since the beginning. You see, the notation is just a shortcut for this. These are the sections, and this should be actually the sections of this. Okay. When are K forms smooth? Roberto, what do you think? When are K forms smooth? They can be smooth as a map from M to this, but they can be smooth also in another sense. Locally, a form is exactly. Locally, a form is this way. These are coefficients, these are functions, and it is reasonable to tell that the form is C infinity when these coefficients are C infinity. So, which definition would you prefer? This one or this one? They are the same. Congratulations, but you already know differential geometry then. Well, this is the theorem. I really hope you have a deja vu feeling at this moment, okay? We already said all of this. You see, we're just repeating. Okay. Oh, you know what? You know that we can pull back forms? Never heard about this? If you have a map from two differential manifolds and the form, differential form on the last manifold, then you have a pulled back differential form. As an exercise, you can try defining it. Okay, we haven't done it, I guess. Here it is written, of course, but you will be surprised that it is really, really natural. And you know what? The same properties. How do you call these properties? What is the magic word in mathematician language? No? Yes, okay, this is linear, but in the more advanced language I'm teaching you, they are the pullback and the vector space structure of forms are compatible. Okay, the magic word, they are compatible. They talk each other. This is really important. Okay, they talk each other. What is a Lie group? It's a group. It's a set with a multiplication. Not only, that's a group. A Lie group is a group which is in the same time a manifold, but this is not enough. You can easily think about something which is a group with a notion which is also a manifold, but the notion of group and the notion of manifold doesn't talk with each other. We do, I mean, I'm not saying we are not concerned about these objects. They are two different objects. We can study them as a group or as a manifold, but there is no reason in studying them as a group which is a manifold if the two structures are not compatible in some way. And when we ask for compatibility between the group structure and the manifold structure, we have the notion of Lie group, because the guy who studied that the first time was a certain Lie person. Okay, so this is the reason. I hope so. And okay. We have the wedge product. I already told you what is the wedge product. Remember when I told you what was the wedge product, it sounded so simple. The wedge product is just the symmetrization, the alternation. I told you, you see, if you have omega wedge tau and you want to compute this on V and W, this is just omega of V times tau of W minus omega of W times tau of V. Very simple, right? Very reasonable. But you know what? On the book, we don't want to make the wedge product only of two one forms. We want to make the wedge product of a K form and the L form. I mean, we need the wedge product between forms, not just this. I'm cheating here because I'm just using the simplest case to define it. If you want to write this on the book, this is the equivalent formula, which sounds much more difficult, right? But I can assure, I wrote, here there is written exactly the same thing. You can see that this minus sign comes from the fact that you have just two arguments, and the possible permutations on two arguments are just two. So the identity and the inverse. But here the possible permutation are a lot, are k factorial, and here are L factorial. And so you have to take the count also of the sign of the permutation. You see? And so then, I mean, it seems it is more difficult. That it is if you're just reading this book without thinking what is behind. So my aim, my duty as a teacher in this case is to teach you how to read these apparently complicated formulas. Okay, as usual, compatibility, relation, important. And I already used this symbol that is omega star, that means all the forms of different degrees, but not as a set, as a union or something like this. I can sum them. Okay, I can take a two form and take the sum with the three form. I mean, it's not not forbidden. I can obtain this this sum, please notice that I don't have n+1 forms on an n-dimensional manifold. Because if you try looking at them locally, you discover that they are given by the x1, the x2, the xn, and then you need another one. But this is a base. So let's put, I don't know, the x2. But the x2 times the x2 is 0. Oh, yes, this is 0. What is the x2 wedge, the x2? Yes, it is 0. And the question is, why? Let's compute it on VW. The x2 of V times the x2 of W minus the same. I mean, I'm swapping them, but it's always the x2. Okay, so you see, if you take a one form and take the wedge of the one form with itself, then due to the alternating property, this is 0, this disappears. This means that you cannot have forms of degree higher than n on a vector space. And so this is a finite sum. And taking all the differential forms all together is a very important point, because on this space you have the differential, and this is the starting point for the RAM theory, for a very important part that we will do in the next year in the differential geometry 2, the revenge. Okay. And oh, yeah, there is a lot of interesting things. Please, when you study, I hope you will use my notes to study them. Use this suggestion. When I write problem 18.8, do it. Do it. I mean, I'm not writing this on every problem, okay? I'm selecting the problems, and usually if I write it, it means that I made it by myself and I decided that this is useful for some reason, okay? And if I'm convinced, I will write general and important result. Okay. Invariant forms. I want to leave some room for questions or something like this. Okay. So you see in problems, okay, this is problem 18.8. This is one I was telling you that is important. Okay. We are almost done. Now, this chapter is devoted to something that we already know, the differential, the exterior derivative, the total derivative, that we already know. The exterior derivative is this symbol d. And we already know that how this is defined on functions. And I told you how this is defined on, for instance, one forms. If the one form is sum of functions times the xi, and this is always the case because this is a base in local coordinates, then its differential is by definition just taking the differential of the functions. You know, in order to use this definition, you must be able to take the differential of a function and take the product with this differential, and this product is the wedge product, of course. This is a one form, this is a one form, and so this is a two form, and so on. If I want to take the differential of a two form, the two form is written as coefficients I now is multi-index, and here I have the xi multi-index with two indexes, okay? And then I will just take the differential of these coefficients. And in the same way, I will have a tree form, and so on. So this means that I have a map from forms to forms. And this map, as I told you, is a map increasing the degree. Okay, the fact that the map is increasing the degree often is written in this fancy way, from omega star to omega star plus 1. Okay, this means that the degree is increasing by 1. And this map, as you can guess, is satisfying certain algebraic properties. In particular, this is a derivation, meaning that when you have the product of two forms, the wedge product, okay, this is in general on a graded algebra, so this is a normal product. For forms, it's the wedge product. Well, this is the derivative of the first times the second, plus or minus, the first not derived, times the derivative of the second. Can you recognize the standard Leibniz derivation rule from calculus, right? In the standard derivation rule, here you have plus 1. Why? Well, now you understand why. Because this is a general rule holding for general differential forms. A function is I told you, a function is a differential form. Which degree? 0. A function is a 0 degree form, so here key equal to 0. And so we have the standard Leibniz rule, okay? Please notice the asymmetry in this formula. Only the degree of the first term count, okay? This is, omega is a key form. Okay, and when you have such a property, you say, since there is this alternation, you say this is an anti-derivation. If there is not this alternation, you say this is a derivation, okay? Well, the differential is satisfying this property. Okay, so this tells you how to do the differential of omega wedge tau. Okay, you just need to know the degree of omega, and you can decompose this differential. And you see, the differential is not compatible in the sense that you would expect. Wouldn't work, actually. This is a form of degree, let's say k plus L. If this is the wedge of the two differentials, you would have plus 1 here and plus 1 here. In total, you would obtain a form which is 2 degrees higher than the form you are differentiating. But you know that the differential is just increasing the degree of 1, okay? I'm not saying this is the reason why this doesn't work, but if you look for this compatibility, in this case, it cannot work, of course, also for this reason. Okay, so the differential is an anti-derivation of degree 1. So you see, this is just a very important language to say that it is anti-derivation. I mean, it satisfies a rule a la Leibniz. And very, very important, actually, the most important of these 3 properties, the differential is always squared to 0. Okay, every degree of differential form. If you take a 3 form, take the differential, you obtain a 4 form. take again the differential, you obtain 0, always. And not only for 3 form, also for 4 form, for 5 form, for 6 form, and so on. This is very, very, very important property. Okay. So I'm saying that if you have K forms, they go into K plus 1 forms, and they go into K plus 2 forms using the differential. And you notice also that I'm always calling it the differential, but sometimes you need to, if you want to be precise, you have to put an index on it. These are different maps, of course. Now, what does it mean that the differential squared is 0? It means that the K plus 1 after the K is equal to 0. So let me check if we... Well, this means the following. Take omega, a K plus 1 form, such that omega is in the image of decay. What does it mean, this? It means that it is in the image, so that there exists a tau in omega k, such that when I do the tau, this is omega. Perfect. And now compute the omega. This means that the omega is equal to 0, is equal to the tau, which is 0 because of this property. And what does it mean? Summing up, I'm saying that omega in image of decay implies that omega, when you take the differential, is 0. So omega is in the kernel of the k plus 1. Okay, both the image of decay and the kernel of dk plus 1 live here. What does it mean, this? Well, it means that the image of decay is contained in the kernel of dk plus 1. Well, when a form, a differential form, its differential is 0, we say that the form is closed. Maybe you already used this word for differential forms on R square. If you take the differential and you obtain 0, you don't say that this is closed. Okay. And forms in the image, we say they are exact. Okay, just the terminology. But the important part of this is that this is a vector space, of course. The image of the linear map is a vector space, right? And this is a vector space. So this is contained here, so we can take the quotient. I mean, when you have something with an algebraic structure contained in something, you can take the quotient space. You can take the quotient vector space. So you can take closed forms, the kernel, over the image. This is a vector space telling you how many closed forms there are that are not exact. Okay? And this property is extremely important. It's an invariant for the manifold, and this is, maybe you heard about it, the cohomology group of the manifold. Cohomology group of M. An intrinsic property is, okay, this is the last chapter of the book, and is something that we are skipping. So this is just the spoiler for differential geometry 2, but just to tell you why the fact that the square equal to 0 is vital in this sense. Okay, so just remember it. Of course, this is the kernel of k plus 1 over the image of k, so this is something that must be indexed with k. Okay, so this is the k cohomology group, and we have the first one, the second one, and so on. Okay, you know, the exterior derivative on coordinate chart is made this way, and we already know it, so we can escape this. And I told you the derivative, the differential is defined this way and so on. Well, if you follow the book, at a certain moment, they say an exterior derivative is something satisfying these three properties. It is an antiderivation of degree 1. It is d squared equal to 0, and on function, it coincides with the differential we already defined on function. Well, now we want to show that there is such an exterior derivative on every manifold. Okay, so this is a theorem, and in this section is devoted to prove that there is such an exterior derivative. I skipped this part, and I already told you how it works on locally on forms. And this is, by the way, how you prove that it exists. And you know, we mathematicians, we are sort of obsessed with the fact when you prove existence, we ask also if it is unique, this existence. This is always important, this fact. Okay, if we define a notion, we want that notion to be clearly defined in a unique way. So the three axioms that I was telling you about the exterior derivative characterize the exterior differential, the exterior derivative of manifold. This is a technical word, the one I use. You see the quotes. Characterize. When you hear this word by a mathematician, this means exactly that this property holds if and only if. Okay, by this property you characterize means that something is uniquely defined by this property. Okay, you see the word characterize. Actually, here it is sort of redundant, saying is characterized uniquely. Characterized means uniquely, but this is more expressive. Okay, what do you think? Exterior differentiation under a pullback is behaving well or not? Yes, it's behaving well. It is compatible with the pullback. And all this section is to prove this. You see? And proof. So the theorem is stating this, and I mean, it's not one line. Okay, in particular, because you have to use multi-indexes, so you have to think about. But if you want to go through the proof, it is useful. Oh, question. Okay, the exercise to prove this theorem in 45 seconds. Please notice that in the beginning was just 15 seconds, but then I thought, no, at this time we are very tired, so let's give them 45 seconds. So the statement is that if I take the differential of a K form and I restrict this to an open set, an open subset of the manifold, then this is the same as inverting the two operations, that is restricting the form to the open subset and then taking the differential. Int 45 seconds. I'm counting in my mind. Okay, I think the time is over. Another hint. Omega restricted to a subset is equal to the pullback by the inclusion of omega. Now 20 seconds.
Differential of the composition. You apply 3 into the omega and then you switch.
The omega equal, use this.
Yes.
So E star of the omega, and then the of E star the omega, but E star the omega again is just the restriction. Okay, congratulations. Oops, what's up? Voila. So the corollary is simply a restatement of the above property. Okay. Okay. Okay, and this exercise. In summary, if F is a C-infinity map of manifolds, then the pullback is a morphism of differential graded algebras. That is, it is a degree preserving, so the pullback doesn't change the degree of the form, algebra homomorphism, meaning that it behaves well with respect to the operation, and moreover it commutes with the differential. Shorter, F star is as good as it can be. Cannot be better. I mean, it's compatible with every structure we have defined on the sets involved. Okay? Now, another section. When we have a K form, we can restrict it to a submanifold. Okay? That means that instead of tangent vectors to the manifold, we are taking tangent vectors to the submanifold. So we are taking the linear map restricted to a subset. This means the only thing you should be aware that also if you have a form, a linear map which was not zero on the space, when you restrict it, if you restrict it just to a subset of the kernel of the linear map, then it can become zero. Okay, so be careful when you make computations. You can have a differential form which is non-zero, but when you restrict it, you cannot anymore assume that it is non-zero. Okay, so this is this can happen. Okay, and can be 0 when the tangent space to S, the submanifold, is contained in the kernel of the form. I'm putting contained in quotes, the kernel in quotes, because the kernel makes sense for a one form, a linear map. When you take a multilinear map, I mean, you have the kernel with respect to single arguments, okay, so then it's not apparent what the definition should be. But anyway, it can become 0. Okay. This is very nice, but okay. What's the time, please? Oh, okay. So, okay. So the over really. We have still one chapter. Okay, this is very nice. This is a formulation of Maxwell equations in this language. Maxwell equations are 4 equations of this kind, but they can be completely reformulated in this way and this way. So they are just the fact that a certain 2 form, this is a differential 2 form, and you can see here the electric field is a 1 form, and the magnetic field is a 2 form, in a sense that it is given in another part of the book and also in the next page here. But the point is that this nice formulation gives you this 2 form, and if you write this 2 form equal to 0, you obtain these 2 Maxwell equations. If you write this 2 form equal to 0, you don't know yet what is this star operator. This is the odd star operator. We will see maybe in the next lecture. You obtain these 2 other equations. So it's a very nice reformulation of Maxwell equation, giving some insight also. Because these actually are the curvatures of a certain connection, and this is in particular called the Bianchi identity, something which is happening for connections. Okay, just to tell you that there are applications of this differential geometry. It's not just abstract things, useless. There are applications. I mean, application to the Maxwell equations means application to everywhere, right? And okay, we are missing something very important, which is the Lie derivative, but I think I will stop here. You have my notes. Please study them and ask me questions. And of course, now, if you have questions.
Do you believe it's sufficient to go through the exercises proposed and examples proposed by the book, or maybe another reference more focused on really practical examples, working maybe also with coordinates could be helpful to understand better the concept?
No, I think this book is perfect also from this point of view. Not only there are practical exercise, as practical as they can be, but for instance, this application to Maxwell equations, I think is very practical. And several of these problems, I guess the more difficult one, are selected and solved at the end of the book. So this can be useful. Of course, if you try an exercise and this is not solved in the book, and you can ask me in advance so I can think how to solve it. I will not answer instantly. Yes, 4 to 5 seconds. And no, I think this book is really perfect.
From this point of view.
Yes, under this point of view.
Thank you.
You're welcome. So I think I can stop sharing so I can say hello. Okay, everybody. Goodbye then.
Maybe just remember when we gather again, when we see again.
Oh, next Monday, next lecture, 2:30. Yes, same time, same format, but we will go through. We are over with this book. We will go through another book where there is the notion of metrics, a book of the same author. I will send you the reference. I think it is already in the program, maybe. Anyway, next week we will insert a new notion in these lectures. Up to this moment, we have never talked about how long can be tangent vectors, about a distance on the tangent space, okay? But this is, of course, important. I mean, up to this moment, maybe you haven't noticed, but up to this moment, a circle and an ellipse for us was exactly the same thing. They are, from the differential geometry point of view, exactly the same. Because the only thing in which they differ is the fact that they have different dimensions on the axis. But we have never talked about the dimension, okay, the length of vectors. Next week, we will introduce the notion of length of vectors. This notion in the language of differential geometry is called a Riemannian metric. Okay.
That includes also the notion of curvature.
And of course, this is including the notion of curvature, connection, and so on. Yes.
Looking really forward.
Yes, in fact, the fact that the circle and the ellipse are the same is no more true because they have different curvatures. And that notion is a metric notion. Okay.
Great.
Okay. Goodbye, everybody.
Bye-bye.
Bye-bye.
Thank you. Bye bye.
Thank you. Bye bye.
Thank you.
Thank you.